Okay, so let's start. This is lecture 21. And in the last class, we were looking at the design of charge pump. So, any questions? So, in the end, we talked about source switched charge pump. And let me just redraw it. Yeah, yeah, sure. You might have asked before, but yeah, tell me. I do not remember second column last part. Oh, there's a delay lock loop, so you get a transfer function of 1. Yeah, you will. Okay, let me. So that is normally used for cleaning. Sorry, okay, let me just put it here. So sorry, this is up and down. You will see the significance of that when we are going to do the delay lock loops. Okay, and so let me just complete this. Okay, and somehow I regenerate this. So what we did last time, this was VDD, this is down, this one I match it here, this one was here, and then this is the last where we tried to undo the view. So this is VBP, VBN. You generate VBN with some other current source, and this one is ground. Okay, and this is goes to the loop filter. So let me just somehow generate this also. This is VDD, and this one is VBN, ICP. Okay. So the question is that we had an assignment homework 2 about the delay lock loop, right? So in delay lock loop, we will look in more detail. That is just for you to understand the phase and frequency variables in the assignment. So one other thing is, let me say you have input signal, okay, of single sinusoidal signal. So let me just write V in is equals to A sine omega naught t. Okay, so this is the input to the system. Okay, and from this input to the system, you want, and this is a single phase input. You want multiple phases output. What will you do? So it's a single frequency omega naught and single frequency and one phase. Okay, and I want multiple phases. This is one example. Why do I need multiple phases? So when you want to sample, so in case of clock recovery loops or any other thing where you want to sample at multiple phases. So for an example, let's say if I have a single clock, okay, and I'm using this clock for sampling a flip-flop. Let me just say this is clock, okay, and the data is here, and you are sampling this at the output. This is Q, right? Now, in case of let's say you want to sample the input data at multiple frequencies. So for this sampling, so let me just say if I am having data of this rate, okay, then if I sample at the rising edge of the clock, it's fine because I am getting data only once in a clock period. Now, if I just tell you my data is something this, So previously it was D, now it is D dash. So what will you do? And you want to use the same clock. One way is you need to have a double the frequency. You can always sample at the rising edge. Here you can say I will sample at the rising and falling edge both, right? You can do that. That is one, like you get two phases. Now if I say no, I have like this, means I want to sample this if required. So what will you do? You need more phases. Either you need more phases or you need higher clock frequency. Okay, so both the things exist depending on which is power efficient requirement. So you may need multiple phases to do this. This is one requirement. So multi-phase clock requirement, clocks required in sub-rate clock and data recovery, you can say clock and data recovery. Okay, this is one. Another thing you can say, when you need IQ phases for multiple reasons. IQ phases you may need for basically pulse width modulation. You may need IQ phases for sampling also. Like IQ, it means this is RF. I think you will still like to generate either with a divider or with an quadrature LC oscillator. But if you need IQ phases, then also you need to do. So the one thing is, either you can divide a clock and generate IQ phases. You can use a polyphase filter to generate IQ phases, but both of them requires a high frequency clock, right? But if I use I think yeah, so divider surely requires you the higher frequency clock to get generate IQ phases. But if I means, now just for an example, if I have, now this thing might not be good for your RF design, but this thing will be pretty good for your can be pretty good for your CDRs. So if I lock the delay of this loop, delay of these four inverters, so TD of these four inverters is equals to one clock period, right? I don't need anything else. One clock period, I can generate multiple phases out. In clock forwarded architectures, where you transmit your data and the clock, you would not like to transmit multi-phase clock. You transmit single clock and you generate multiple phases at the receiver end, and you can do that. Okay, it so if you are transmitting the same frequency clock which you can use with the multiple phases, then it is, you can use a delay lock loop. If you are transmitting a low frequency clock, then you need to multiply. Okay, any more questions? Yeah. So RF and wireline, the difference between the two is that the spurious tones are very much important in case of your RF application. So let me tell you, okay, this is slightly going out of context, but let's say I'm having carrier FC, which is surrounded by a phase noise. Okay, so the phase noise, whatever the spectrum is, phase noise, and then I have spurious tones. Spurious tones means unwanted tones on either side of FC carrier, other than the phase noise. And I can have a lower phase noise, let me just say, but more tones. This is one case. The other case might be that I am having a higher phase noise or tones also. So consider both the cases for RF application, RF and broadband. For RF application, your spurious tones can down convert your signals I'm talking of the receiver right now. So you have a signal at a one particular in a narrowband signals, and all other channels are occupied by the other signals in the spectrum, right? They might not be the required signal. If you have a huge spurious stones in case of the clock source which you are using to down convert, so what do you have? You have an incoming signal, RF signal, desired RF signal, which is narrow band, which is something. So this is, let's say, desired, and all other junk is undesired, and you can have a blocker sitting at all different frequencies. Now, if you use a clock here which has huge spurious tones, okay, but maybe a smaller noise floor like this, the spurious tones will mix with your blockers and down convert it. So the requirement for RF application is not only on the phase noise, but also on the tone values. What is the tone? How many dBc? How much dB it is away in given band? So if you look for any specification for your RF signals, they will specify that any tone should not be more than certain value within this bandwidth, and when you go further away, it's like different. Now, in case of wireline, your signal is very broadband. Okay, so this is like the signal is sitting at DC. So let's see this. In case of broadband application, my signal is sitting all through. So normally the clock, so let me just make it here. Okay, so your FC is here, and your most of the energy is concentrated between FC by 2. This is a broadband signal. When you have spurious tones, what you will have, so you have a phase noise, and on top of that, you have the spurious tones. Okay. So these spurious tones itself appear more means either whether you are looking those spurious tones as a single tone or you are looking them as a contribution to the jitter. Right? Both are the same things. It's just that the way am I looking at it. So in case of broadband, the total jitter is much more important than a single tone. Means you should not make the single tone also equal to the main tone. That's a different. Then you will have more. And your CDR has to track that. Okay. Whereas these tones are not doing the same thing, down converting thing which you are seeing in the RF case. Yeah. So that is down converting the noise, but you are not having any like big nearby interferer or blocker sitting just at the spurious tone, which will just make your signal to lose all the sensitivity it has. So this is slightly this is the difference when you are designing a PLL for an RF case and when you are designing a PLL for a broadband case. That in case of broadband, you look for the total integrated jitter or total jitter on the clock. The spurious tones are not that much important, I would say, but just do not basically make them equal to the main tone also. Somewhat dBc, like 40 dBc references per spurious tones are good enough for many broadband applications, but they may not be that good. May not be that good for a GSM application. Okay, so in case of means 10 Gbp, if you look at 10 Gbps of broadband application, you can if you can in a given technology you will use a ring oscillator. Okay, and that might work fine. Again, depending on a standard. Whereas 10 Gbps, I think for all the RF requirements, even for 2.4 or even 0.9, you go for LC. Lesser tones, and it's very much important to look at the spurious tones in case of RF applications. Okay. So this delay lock loop, ring oscillator based delay lock loop, ring oscillator based multiplying delay lock loop, fractional NPN, and all these things will be pretty common in broadband, may not be that common in case of high speed RF applications. Okay. Any? Yeah. Why? There is an integrator in the loop or no? Pardon? Okay. Yeah, so let it be that way. But I think there is an example for type 2 also when you, it's like when the op amp is there. That's the question, right? The fourth part is the, okay. So one thing is, means if it's a lag leak filter you have, means just you want to have a 65-degree phase margin, you go with that. There are four options in that or it's only one? I do not remember the problem as such. Okay. Fourth one, what is the filter you have? Okay. This one, right? And you're taking this one. Yeah. So means you try to see whether you get 65-degree phase margin or you get 90-degree phase margin. Okay. Now what's the problem 5 as such? So let me. So I would like to means do that in a more like calculation with things, and I will give you the solutions, and then we can discuss it in the class. Okay, because that will be more involved thing. Yeah. So where is the submission as such? Are you submitting assignment or no? Okay. Okay. Now send us something which I can understand. Okay. Yeah. Okay. So let's come back to where we were. Okay. So this part goes. Yeah. So we looked at a source switch charge pump, and at the end of the today's or the last class, and to reduce charge sharing, we have up is 5. So this one is up signal, right? No, this one is up bar, and this one was down. Yeah. And this way we fix the. Okay, so let me just mark it with a different color here. Uh, this way we tried to reduce the static mismatch between the up and down currents by using the feedback. Okay, and you have to compensate this feedback loop such that it doesn't oscillate. Okay, now still if you look that in this charge pump, this part of the charge pump means you get all the bias, but the MOSFET which is acting as a current source, M1 and M2, that sees a variation in its drain and actually a source potential. So it goes from cutoff to saturation region in this case. Okay, so that limits, the first thing is that limits the speed for sure, and then you will have surely have some delta variation between the up and down currents. On time mismatch will be there no matter what we do, because we cannot make the PMOS as same as the NMOS. Okay, so now let's see what's the, so in this case your PMOS and NMOS current source means if you are operating at a lower speed, then for the larger time it's the same as you desire, but during the transition you will see a difference in these cases in both the up and down currents. So PMOS and NMOS current source here go from switch between your cutoff to saturation region. Okay, which surely will limit the speed of operation. An on time and off time mismatch will be there. Sorry, not on time, off time. This on time mismatch, T on mismatch between up and down current source. up and I down. Okay. So what can you suggest? Now comes the speed requirement. So what can you suggest I can do to this charge pump so that my current source doesn't switch? It remains constant. So let me start that I have, so if I do not want to switch a current source, I have a fixed current source, both top and bottom. So I can put PMOS at the bottom. Okay. So VBP, VBN, this one is ground. And now I want to switch the current. So now the switch comes here. Now this is the same thing which we started there where the clock feed through was important. Okay. So that's why this is like a drain switch charge pump. But this will be different from the one which you have seen before. So I can have, okay, maybe this go to ground, or let me just put it this way, not go to ground. Up bar, down, up, down bar. Okay, ICP. Let me call this node as VY and this is VX. So what's the difference between the gate M0 and M1 between the drain switch charge pump and this charge pump? Current source is always on, right? So in this case, your current source is always on, so you will not see the transient nature of the current source which was a problem before. Your current source mismatch between the up and down. Okay. But so the thing is, in one case when the current flows here, and in another case the current flows on this side. Okay. But what's the problem? Pardon? Okay, so this has a static power consumption, right? But the other thing is this will be faster because your current source is not doing the cut on off to on transition and on to off transition, because Vx, if you look at it, faster your transients at Vx and Vy nodes are limited. So let me just write this, switching, and transients on Vx and Vy are limited. Now, what is the mismatch between up and up bar? Yeah, any timing mismatch between up and up bar will give you a delta I. So we want to up and up bar to, that's why I'm using both the PMOS on both the sides. I could have also used NMOS and the different signal. So surely if there is a mismatch between up and up bar, this will give you a delta I at the output. So you have to ensure that up and up bar are differential in operation. The other thing which you can say in this case is that your up and down signals, right? These signals can be limited swing, that they do not need to be CMOS signals. Now, how do you generate it? That's a different case. Can be limited swing. Because if we recall the previous case, right? In the previous case, we had the up and down signals as large swing signals, which also cause the clock feed through. So here also clock feed through will be a problem, but you can limit it by limiting the swing. So if you look at the positives and negative of this particular design, what I have is current source is always on, that is negative. Okay, static power consumption, these two are the same, and faster in switching, that one is positive. Transients on Vx and Vy are good. Up and down signals can be limited swing, and another thing is how do we generate it? Clock feed through is surely a problem. Okay. The other thing is you will see that in one case the output of the current source, sorry, this Vd is different from Vd here. Vd of the when it is conducting on the other branch. So it is not that symmetric. Okay. So ideally what we want that if Vy, so let me just make this here. We do not want Vy to change. But in this case, Vy is surely going to change because you will see the channel length modulation for the transistor. Let me just name them. So this is M2, M3, and M2 dash and M3 dash. Okay. So we will see the problem that we will see transient at Vx and Vy node, which we ideally do not want to see. Okay, and why do we do not want to see? Because those transients will affect the delta I current which goes into the loop filter. So an easy fix for that is that I connect these two. So sorry, let me just connect in a. So I remove this from not this VDD and ground connection, but I just make this connection. Okay. Now, who ensures that VD on the right hand side is the same as VD on the left hand side, VD dash? Huh? So you want me to put a resistor here? Let me just go and say I have put a resistor here. You want to do this? What will this do? Think about it. When you are in the off state, your any delta I current will go into the, pardon? Okay, so let me just go and put a switch also. Where do you want to put the switch? Okay, so I want to put a switch in place of resistor. So when will this switch be on? When charge pump is on, that this is just a floating thing, right? So what you are saying is, so let me just try to see. So what you say is, let me just say, now this signal V, let me call this as something VA. So this VA should be your logic when like both up and down signals are high, that time it should be high, or how? Can I do this up and down? Means can I use this signal? So this is like in terms of logic signal which will be up dot down here. In this case, this switch will be on whenever your up and down signals are high. What is this doing? Any delta change in VCM is going to affect the total current which is going into the charge pump. And you are switching it at every reference, so you are injecting some delta every time. So that might not be the that good reason to, that might not be a good fix for this. Okay, so let's remove this and remove this thing. What it means, yeah. Okay, that sounds pretty bit complicated. So what you say is I can put an op amp where? Okay, let's do this. So I have an op amp. Okay, and this is VD and this is VD dash. And what do we do? That is interesting. So I have this Vx and Vy. What is the potential are you thinking will be at Vx and Vy? Just guess. One is the NMOS drain, other is the and one is the drain of the NMOS current source, other is the drain of the PMOS current source. And this is an output of an op-amp which has to operate linearly. So what are we trying to do here? Let me just say. First thing is you would not like this op-amps. So if you can, let's say VD and VD dash, any common mode. So you have to detect the common mode or do something. Not the common mode. So let's say do it this way. First see what's the requirement before fixing this. So I have a loop filter, right, whose DC voltage is actually this. V control, let me just call this as 0, and this is V control node, right? So the DC voltage of this loop filter will vary as per the requirement of the loop for the frequency. That's as simple as that. Okay. Now this V control DC voltage can vary within your plus minus delta F of your PLL frequency range, right? What we wanted VD dash also to vary in the same manner, so that when the current switch this way, you do not see much transients at Vx and Vy, right? So this is right that you want to equate Vd and Vd dash, so both are the inputs to the op amp, but controlling Vx and Vy would not be the better option. Yeah, so the thing is, yeah, that's also another interesting thing that I can go. So what you are saying is, let's say I have this thing and I have another here. Now what's the problem? Let's see R and C1, R and C1. But can you still, without using any op amp, can you still ensure that VD and VD dash are equal? You can't. Okay. So you have to use an op amp to fix this thing. But let's say even if I go the way you are saying to have the symmetry on the either side, what's the problem? Anything? Area. C1 is one of the biggest cap in the PLL in the range of depending on, and it can go from few picofarads to nanofarads, and you will just double the area. So you would not like to do this unless you are using a differential loop filter for some reason. Okay, so this part you do not do it. So you have to use an op amp to fix the loop filter. So let me leave it for as an exercise. Figure it out. How will I control this means? So let me just say, figure out by the next class. I will talk about it later then. So what we should control such that VD and VD dash are fixed, or any quick you can tell me. Pardon? Okay, so let's do this as you say. So I have an op amp, okay, which is this. This is VD here, and if you are talking about this, and this is VD dash. Okay, you can do this. So I left it for the next class. You just told me right now. So if you use a source follower, you can fix that VD and VD dash. Okay. You good question. Tell me which way we should be connect. If VD is coming on the loop filter side, do you want to add an output impedance of an op amp there to change your loop filter gain? Or you want to take that the input gate captions into account in your loop filter and get done away with it? And first other thing is, what parameter is changing in the PLL and what do you want to change? See, the cause is not VD dash. The cause is VD. You get that point? So the thing is, VD changes because of the large range of the PLL, and you want to, that is the cause, and you want to fix VD dash for the charge pump. It's not the other way around. So you want to say whether I go with the C1 or you want. So at DC, there is no drop across R1. At DC, there is no drop across R1. The only thing is the delta I current is going into it. Okay. In case if you are taking if you are taking C, then you should consider the filter which is existing at the gate node RC. So let me just say. So this is one case. The other case will be where you are saying I can. So let me just bring C2, C1. What you are saying, can we do this? Right? This is V control node, right? In both the cases. Yeah, just you can check that thing as such. No, so the other thing is what you want to fix from this. You want to fix the dynamic. You want to fix the dynamic range of the PLL. You do not want to change anything transient. Means if there is anything. So let me just say this. There are two different cases. One case is when your F out is equals to, just for example, let's say 500 megahertz to 1.5 gigahertz. Your V control might be 0.25 to 0.75, and you can lie anywhere in between depending on the frequency range. So whichever point you pick, based on that, your V control will change, right? In a steady state, the V control node has to be this only. And I want to change the PMOS, the drain voltage of the left hand side, such that I do not see much switching at Vx and Vy transients. So the operating condition should be same. So we want to fix that. What we do not want to fix it, so let's say at every reference frequency, something is injected into the loop PL, into the loop filter. Means, let me just put it this way. So at every reference frequency, no matter how matched it will be, because of some mismatches, you are going to inject these kind of things. So when you inject these currents onto the charge pump, your V control voltage will change accordingly. You are not changing the PMOS current source. You're not changing the drain voltage for that. Okay. Because if you see, the average of that is still zero in a steady state. You're not changing that particular thing. So the bandwidth of this loop should be greater than the PLL bandwidth. Okay, if it is much slower than the PLL bandwidth, then you will see much difference. Okay, but it should not be high also to start changing. I won't say it should not be high also. Means if you are having this thing, this kind of bandwidth, then it will try to change VD dash also. But that's not the motive. The motive is to change this the whole range of the PLL. No, that's what I'm saying. Bandwidth of this op amp in this configuration should not be less than the PLL bandwidth. Okay, if it is greater than the PLL bandwidth, much greater. So one thing is, these things can only be tracked only if you have the bandwidth much greater than the reference frequency. Okay, but the thing is, do you want to track that? Or if you track that, what's the benefit? If you do not track it, what's the benefit? You can check that particular part. Okay. Right. Yeah, in a steady state, there it will not be any mismatch if the bandwidth is too small, right? But if you are doing any kind of frequency modulation or something, you will see that mismatch. You will see that value. So what he is saying is, if the bandwidth of this op amp which we are using to track the VD, if that is too small, let's say that bandwidth is very much smaller than the PLL loop bandwidth, then if you change any frequency at the input, the output frequency will get changed, okay, at a large amount of time after that, and then the steady state at that operating point will not be a problem in every. But the thing, so for sure that is the case. But if you are doing any frequency modulation on the PLL, okay, then this bandwidth of the loop will be problem. So one other thing I can tell here is that in the PLL, because this is a sample system with the reference frequency, right? So if you are in most of the cases, if you are changing any of the frequency of the output PLL or applying any phase change to the PLL output, you will be applying those changes at reference frequencies. Okay, faster than reference frequency will not work here because this is sampled at FREF. Okay, so now the thing is, do you want to track that or not? Okay, so there this bandwidth will come into question. Much lesser there, I do not think much lesser bandwidth. If you just leave it one time frequency change, it will be any. And any bandwidth will always come with a trade-off of your power. Okay, so this is differential charge pump which you can use and which will be having a least mismatch. Means least mismatch in the sense I up and I down on time mismatch, because you're using current is getting steered. The current sources are not making any transient, any on off thing, and you are taking the VD also into account. Okay, so here we do not need any switch to retain the one which we were using in a source switched charge pump. We do not need any. This means this is coming as the other part of the branch. Okay, so and again this up and down signals depending, you can use a low swing signals here. Okay, so that completes the discussion on charge pump. There are other charge pumps also. I think we can look at it once we have some more time on this talk. Okay. So the next topic which I would like to start is another thing. So the thing, okay, let me just say the loop filter one for right now. This is very brief, which I will talk about it because I want the you guys start designing PLL. So right now, just limit yourselves to passives. When you are using a RC, there will be problem with the active devices. We will look how to deal with them later. So this is the loop filter for now. Okay, we are your RC and they are all passive devices. Do not use any active devices because then you will see some problem coming in. So in case for large phase margin, let me just say, do not get scared if you get large phase margin will lead to your large C1, and the C1 can go, means I have to see what numbers you are going to design, means it can go up to 100 picofarad easily. No problem. When you're designing PLL up to close to let's say 5 gigahertz or 8 gigahertz kind of PLL, ring PLL. So do not get scared with when you see a capture number of 100 picofarad right now. Okay, there will be ways how can we realize a larger caption without using a smaller, by using a smaller captions. We will look that into later once we get done with the oscillator. Okay, and resistance is normally you will decide based on noise. Resistor choice is based on noise mostly. So resistance values may not go beyond 5K, 10K for a noise value, no, jitter value of close to 1 to 2 to 3 picoseconds RMS up to 5 picosecond RMS. Okay, and do not use your MOS register here or something. Means you can try to do this. So right now means I would say do not do these kinds of things. Let's say if I go and use all active devices, okay, and this is also becomes a okay. And interesting, you can say I'm using a very less area and I am doing this. Gate captions on both the sides. Okay, so can you just tell me what the issues will be? We will deal with the issues later. Gate leakage. Pardon? So no, what you are saying is this. Are you saying that if I try to realize this capacitor with the MOS capacitor, the equivalent circuit will be some capacitor plus a resistor to ground? How many models and schematics have the substrate? Okay. So few will be there right now till you surely I agree with you that all these capacitors will come with a resistance, but look at that how much resistance at what frequencies are you working at. Okay, sure, that is the case, and that will give you the leakage path and leakage current, and that leakage current, so good that we brought it here, leakage current in active devices, what will that lead to? Yeah, everything leads to spurs only here. Leakage connective rises. Okay, so let me just say that. So the important part is, let me just show. So, okay, doesn't make sense here. So if I have a I leakage current, every reference frequency, let me plot a reference here. Okay, so this is a reference, and if I have a I leakage, that might be some positive or some negative throughout. I'm just plotting the I leakage. It will be very small. Sorry. So let's say this is I leakage. Actually, it is all the way same. So this is reference 0. And I have a I leak some delta value all throughout. That will be the leakage due to active devices. Okay. So I leak. So what will be the response of the PLL due to this? No. Pardon? Adjust the up down timing. So what should be the up pulse? Means just we are just right now considering only the leakage. So up pulse will be something here, and I plot it as a negative thing. So down pulse will be somewhat this. Okay, assume that there is no mismatch between I up and I down right now, up and down. So what is this T offset? Because of the leakage current. So let's say I up and I down is equals to same. So let me just bring that I up is equals to I down, I charge pump I call that, and I leakage is surely much smaller than ICP. Let me put it this way. Okay. So what is this T offset here? There is, yeah, let me just write it. I up minus I down. Divide by, okay. What did I write just above that equation? I up equals to I down. So, means what you are saying is right. It basically the time period for which the current is being pumped to. So that's why I wrote. I say there is no difference between I up and I down. I can just say ICP. So T offset is equals to your I leak by ICP times Tref. Okay. Now this T offset will, you can calculate this per in the same way as you calculated this per for others. Okay. So most of the time, if you want to realize a really good analog PLL, you would not like to use these active mass capacitance. Surely, capacitance of these two means that is another problem. Means you can say capacitance, active mass capacitance is dependent on gate control, right? Active mass capacitance is dependent on control voltage. That is the problem. But I would say that may not be, yeah, that is the leakage is also dependent on control voltage. So all these things parameters will vary. So your capacitance changes depending on the control voltage, your bandwidth changes. Okay, your leakage causes you the other problem itself. So if so, one way is either you try all the ways. Okay, if leakage changes, I will push in more current. If mass capacitance changes, I will switch on more capacitance. Means I can adapt my cap accordingly. So you can do all those things, provided they give you the enough benefit. But what I was trying to say is that those things using a mass capacitance is actually may not be a good idea if you want to realize a really good phase noise PL. So you go with the means there are other ways to realize a larger capacitance while using a smaller value. And I think I actually want to do oscillator because that will help you to do PLL design. So let me just tell you. So you would have seen this circuit, right? I in, V out, whatever you say, and then this is gain of ampere. See, you know the circuit, right? That by using a smaller capacitance, I can realize a larger capacitance. And this capacitance can be your passive. If capacitance becomes a real big problem, let's say it goes to 1 nanofarad or something, I cannot spend that area on the passive, I may go this approach. But the basic capacitance element which I am going to use, I would try to have it as a passive. Okay. So we will deal with this loop filter to gather all the variations once we are done with the oscillator, because that will help you to design. So let's stop the lecture here.